Hello operating systems people, this is Gabriel Palmer, and today we're going to be talking about crash consistency. This is something that's very important in file system and maps very well to actually how reliable we think that file systems are. And the big question that crash consistency is always asking is, what if we unexpectedly lose power? So if we're doing a lot of different operations on our system and we lose power, what does that mean for the state of our volatile storage? We know that CPU and DRAM lose all state when they lose power. DRAM actually requires 30 millisecond refreshes of its data to not lose that data. So of course, if you aren't providing the power for those refreshes, the data goes away. So we rely on disks, we rely on SSDs, we rely on non-volatile memory for non-volatile storage to maintain data across power cyclings. Cool. So it seems like the answer is easy, right? Just store everything on disk. Yeah, of course, everything gets more difficult as you dive in. So let's actually try to understand the complexities of this issue before we dive into any solutions. And I do want to say that I'm going to be using the word disk within this lecture, but most of these issues are the same for rotating magnetic disks or solid-state disks. There are some additional complexities there, but for the purposes of this, I'm just going to refer to disk, and you could think of it as being either of the two. Okay, so we're going to be using this as kind of a running example throughout the entire talk, and this is a disk layout including a lot of different structures. So on the far left you see a number of bitmaps. We're just going to assume that there are separate spaces on disk for inodes, separate spaces on disk for bitmaps that track kind of whether inodes and disk blocks are free or not, and separate places on disk for the actual data blocks themselves. So we have two sets of bitmaps, one for tracking which inodes have been allocated or not, and another set of bitmaps tracking the actual data blocks themselves. So let's just imagine this relatively simple style of disks that does not have inodes interleaved with data blocks or anything like that, and just uses bitmap-based free space tracking, right? Okay, so you can kind of see a lot of that labeled here. Each of the inodes here has, of course, all of the metadata about the files or directories. That includes permission sizes, and we're going to assume a very simple inode structure that doesn't actually have an external index stored in data blocks itself, and instead just has a set of single indirection pointers to the data blocks. So the inodes are relatively simple. A lot of what we're talking about today will get much more complicated when you actually have inodes that include index blocks, but not in a way that is relevant for kind of your understanding these issues. So we can see in this example that the third inode is active. It's a darker color, and the bitmap corresponding to that is also darker. And kind of the same thing for the data block, right? The data block is active, and therefore its bit is set to a darker color. So hopefully you understand this correspondence. Also, hopefully you can see that the inode, it does have this data array of all of the blocks constituting the data for that file or directory, and we have an arrow effectively pointing from the inode to the data block that it actually has inside of it. Okay, given that setup, let's actually consider some simple examples. Are there problems when we do reads from the disk with losing power? Okay, so we're just doing a simple read here. We're going to try to read in the inode block, and then we're going to try to read in the zero data block within that inode, the data within the inode, right? And this is a relatively simple operation. We're just trying to get the data of the file, no problem. So first we're going to read out the inode block, then we're going to read out the data block itself. Now the question is, if there's a crash that happens effectively logically in between when we receive the first read and when we receive the second, does anything bad happen to the actual disk, to the data structure on disk? And you'll notice here that because we're just reading data out, not much actually goes wrong, right? It's hard to put the disk into some sort of a bad state when we aren't actually writing to the disk. So read is actually, most read-based operations are not an issue. So let's go on to write. So here we're appending onto some file within the data system, and we're adding some data of some size, okay? So first thing that we need to do, since we're appending and adding to the data, let's imagine that we need a new data block, so we need to ask the bitmap to do an allocation. And we're going to allocate, we know that the bitmap has a free allocation at block n, so we're going to allocate block n, setting it in the bitmap. Then we're going to initialize our inode in memory to have its own size plus the size of the data that we're actually writing to the file, and then we're going to add the new block essentially as the second block within the file. There's a lot of logic, of course, here in how we choose a second block that I'm completely avoiding, but it's not that big a deal. I'm not going to go over the details. Okay, so then what do? We update the block, which is to say we want to write the data out to the new block that we've allocated. Then we want to update the inode with its increased size and the pointer to its new block. Okay, so what does that look like? We have one block write to the bitmap that you can see bolded at the top, where we are allocating node n. Then we are actually updating that node with the data that we're writing into it as a second update. And then the third is, of course, updating the inode itself. And now the question is, what happens if crashes happen between any of these operations? So let's choose a relatively simple way to think about it, where we have the following operation, right? So we have this crash, but it happens right after the bitmap allocation, and before we do any of the other operations. So you see visually, using kind of the, this didn't happen insignia, that we are only conducting the first store and not the second or the third, right? Okay, so what could go wrong here? What looks like it's wrong here? Think about it for a second. What does this mean for the data structures on disk? Think about it for a second, pause, come back. Okay, so what's happening here is, of course, we've said that a block is allocated in the bitmap, which means that future allocations will never try to allocate in that block. So this effectively means that when we reboot the system, that bit is set in the bitmap, but none of the inode or the data is put into the block. So therefore, that disk block is effectively never going to be used again, so it leaks, right? We have a storage leak. So this is a problem. We have an inconsistency with the data structures within our file system that leads to some awkwardness, right? Okay, let's think about what happens if we have a crash here. So we update our bitmap, we update the data on disk, but we do not update our inode. Well, okay, pause, think about it, come back. So what happens here, of course, is that our disk block leaks just the same as before, and we've updated data onto the block, so it's initialized now to some useful information, but it's not tracked in any way. It's not plugged into the file system by being referenced by, in this case, the inode that we want it to be. So this is a big problem, right? Okay, now we're going to reverse the order of some of these operations. We'll see a little bit later that the order here actually doesn't really matter. We're kind of framing this as what happens if a crash happens between these two lines. You'll see that effectively we can have any interleavings of these updates. So we need to consider them all. So logically, I'm just going to reorder them a little bit and put the update inode at the top, and then kind of the bitmap allocation at the very bottom. Okay, so updating some of the order of these operations. Okay, so what you can see is first we're updating the inode, great, and then we crash. So you can see that the inode has a new arrow pointing out to the data block because it was updated, and its size reflects that. So what is wrong here? How is the file system inconsistent? How is that going to impact the system? Pause for a second, think about it, come back. Okay, so the big problem here is that our inode references uninitialized memory that has not been allocated yet. This is a huge problem. This is effectively akin to a dangling pointer in a memory-based system that we think of as just kind of a typical programming problem, a dangling pointer. We have a pointer within the inode, a reference that points to a block that hasn't been allocated. Therefore, in the future, it could be allocated for a different purpose, and we will reference it as part of the file. So we could allocate that disk block as part of another file, but this inode will reference it as part of this file. This is a huge problem, right? And even if that doesn't happen, and we access this file, we will access a block on disk that is pointed to that has not been initialized with any decent data. So we'll actually also access uninitialized data. So this is a huge problem. So let's look at the next thing. We update the inode, we update the block in memory, but we don't update that bitmap. So kind of the same thing, right? Think about it. What's the issue here? Pause it, come back. Okay, so what happens here, of course, is we still have the bitmap problem. At least now we're pointing to initialized data, but it's actually not useful. That doesn't actually buy us much, because that node, that data block that we allocated data into and wrote data into, because it's not tracked in the bitmap as allocated, in the future, after we boot up again, we could reallocate that block for a different purpose, completely override this data that has been initialized in the storage right now, and then access it accidentally through this inode that we see here. So this is a huge problem. We can see that when the system crashes, things go really, really wrong. Right? Our file system starts getting into a very bad state where we don't really know what's happening. This is bad for programs, but with programs, we can always just reboot them. And, that's fine. Great. We rebooted it, and now we can run it again. The previous problem is gone. However, a file system is persistent. You have to live with the problems in that persistent medium across reboots. There's no nice kill your process for an entire file system. So this is a big problem, that if power is removed from the system, the file system suddenly effectively becomes unusable or is incorrect. Let's consider an even worse problem. So this is the rename system call or something like it that's used by the move program that you can execute at your shell, right? So you can see we're moving B, that is within the A directory, into the C directory, right? So diagrammatically in the picture at the top, you can see that we have two inodes, one for A, one for C, and we're effectively trying to remove B from the A inode and add it into the C inode, right? So this is what rename effectively does. It just moves from one inode into the other. So in code, you can see that we're trying to remove from the directory inode A the entry for B, right, for our B file. And then we're trying to add the entry for B into our directory inode for C. And that entry corresponds to inode B, right? So we're moving B into C, right? And you can see at the very bottom, this is effectively, the dark arrow is what it looks like right now. We have a pointer from A to B, and we want to change that to effectively just having an arrow from C to B. Okay, and this is effectively going to take two writes, 1 and 2, as we see at the bottom, two updates to the disk. Okay, so if we crash between these two operations, we have a huge problem, because we have removed the entry from B in A, but we haven't added it to C. So B just magically disappears from the file system completely, right? This is a huge problem, because now if B is a subdirectory, we could have just completely lost an entire subdirectory on our disk, right? This is a massive problem, right? So we need to figure out some way to do better, right? Yeah, I'm sorry. I think I misordered these slides. No, I didn't. Okay, so in this case, I've just reversed the operation. So first, we are adding B to inode C. So we're adding the B file or directory into the C directory. And then we're removing B from the A directory. Okay, but what if a crash happens between these two operations? Think about it for a second, pause, come back. Okay, so what happens? Well, we've added a link from C to B, but we still have a link from A to B. Now we have two references to B, both in A and in C. And this is a problem because every single inode usually maintains a reference count. How many references are there within the file system to that inode? And if you remove all of these references, then you're supposed to be able to deallocate the inode. But in this case, we have two references to it, but only a reference count of 1. So all of that logic around the reference count tracking is going to be incorrect, which will cause later problems as we delete the file or directory once, but there still is another reference around. So this is all a huge problem and really motivates that we need to be very careful about how we structure our updates to the disk with respect to our file system consistency. Now, I want to point out again that this is not necessarily a problem like for synchronization, where we can look at the order of the different operations that are being performed and just say, all right, if a crash is in between these two lines, what happens? In between these two lines, what happens? Of course, I did that in a previous example, but here I want to show you that it's a more generic problem. We know on the left that we have our VFS, which includes our create, read, open, write, close type calls. Those are implemented for a number of different file systems, and those file systems do reads and writes to blocks on disk. And of course, those get made to the actual OS buffer cache. And this is again just a cache in memory that holds a lot of disk data to make it more quickly accessible. So as we update all of those structures within the buffer cache, it may happen that any updates that we do get reordered within the buffer cache or within the layers of the operating system that are sending the requests out to the physical disk. So any of these requests, any of these writes that we do to the disk, they may get reordered. So yes, I was choosing kind of these lines within the code previously and said, what if a crash happens here? But really, it's for all of the writes that you've issued, if you haven't done anything to prevent it, they could all be reordered, right? So this reordering can happen on all pending reads and writes. Okay, so given that, we really need to solve the problem of how to keep our file system on disk reasonable and correct. And this is a notion called crash consistency within file systems. And the whole idea here is that upon crashing, the file system must at all points in time be in a valid state. Valid state can mean a lot of things, but it must include, for instance, that space isn't leaked or wasted in some sense. I don't mean waste here as in like external fragmentation. I mean like the bitmap is not updated to reflect or the indices are not updated to reflect that a bitmap for allocation has been updated. You can't double reference directories or files when they only think that they have a single reference. You can't lose references to directories or files. You must properly update all of the file and directory data, etc., right? So these are all the things that we would think of our file system being in a valid state. And this maps well to a notion of consistency. Consistency is a set of invariants that we lay on top of a data structure to determine whether at some point in time it is correct. And you might think that a consistent, circular, doubly linked list that has, previous and next pointer and it's circular, so the last entry in the list points to the first and the first back points to the last, would have simple invariants. These would be that whoever you point to next has their previous pointer pointing to you, right? This is a very simple invariant, but that alone captures most of the structure of a circular doubly linked list. So if at any point in time that linked list does not have that invariant, the next node that you point to its previous points to somebody else, well, that's a problem. But of course, while you're updating the linked list, you're going to cause these inconsistencies. So you want the linked list to be consistent when you start to access it, not when you're actually making the modifications. We have something similar here. We want the disk to have a consistent value such that its data structures all make sense, even though we're going to be modifying it in the meantime and making some updates. However, once we want to be able to understand the contents of disk as being consistent at certain points, right? So the question that we want to ask now is simply, how can we design our file system such that we can either fix up any inconsistent or invalid states within that file system because of these kind of crash problems that we talked about, or can we design our file system effectively to avoid those inconsistent states in some sense? And ideally, what we really want to provide is some notion of being able to atomically update the system, which is to say we have multiple updates to the disk that should be able to go through and effectively, if we have a consistent state for the file system before those updates, then we want a consistent state of the file system after those updates. And we want to be able to make all those updates all at once, or effectively none of them, which is to say atomically. Okay, I talked about a lot of valid or invalid states here. I want to just, again, give some examples of invalid states for a file system. This could be that the references to an inode do not match the reference count. It could be that you have multiple references to a data block, two files containing the same data block. That doesn't make any sense. You could have free blocks that are referenced, which is to say a free list bitmap was not updated to say that a block should be allocated. So this is effectively where free blocks are referenced by inodes but are free, right? This is a dangling pointer equivalent. You can look up what a dangling pointer is if you want to see what it is in a memory-based system in C. You could have the allocated blocks are not referenced, which is kind of the inverse type of a situation. This is a storage leak. So you have allocated blocks that are not referenced by any inode, so we're never going to free them. Therefore, we're leaking that storage unit, never to reclaim it. You can have inodes or indices with illogical contents. This is just corruption of data structures on disk. And you can have references to uninitialized data blocks. And this is kind of like uninitialized variables in C. So you can see that a lot of these, again, they define kind of what we think of as consistency or not, right? Okay, so the first solution that we're going to talk about is actually the traditional solution. This is what we got by with for, 30 years, effectively. And that is fsck, and this basically says, let's have all of those problems that we just saw. Let's allow them to happen. And when a crash happens, have the fsck program run, and it will walk all through disk and try to identify all of those potential problems that we identified and try to fix them up as much as it can. So for instance, it will walk through all of the inodes in the system when they boot up. And it will look to see how many reference blocks there are, which blocks are referenced, versus whether there are marked as free within the inode or block bitmaps. So if you have a block or an inode that's referenced by an inode and it's free, then you have a problem, right? You need to mark it as allocated. So you might be able to fix up the bitmap in that case. You have a number of inode references that don't match the inode reference count. It's hard to know why this happened in all cases, but maybe we just fix up the reference count. And then you have greater than one block greater than one reference to a block from multiple inodes. Again, this is an inode kind of, or a block of data being stored between different files. This is really bad. We can't have this. We need to detect this type of case and maybe just copy the block so it could be used in both of the files. This is not a perfect solution. This does not actually detect all problems. It does not fix all errors, and it takes an awfully long time to run at boot because you literally have to walk through your entire disk in some cases to be able to figure out what happened, right? At least you need to walk through all of your bitmaps and inodes. So this is not great. fsck, it was actually something that we lived with for a very, very long time when disks were relatively small. But when they grew up and they got huge, the amount of time it took to actually do an fsck on one of those disks was not maintainable. It was, in the hours to days type thing, depending on the size of your disk. So we needed another solution. Luckily, one had been around for a long time. It just wasn't kind of adopted in a lot of different domains. So we started actually using it, and that's called journaling. ext2 is a good example of the previous type of a system. ext3 was basically adding journaling to that file system. And the idea behind journaling is that we break the modifications into two separate stages. One, where we try to write the changes that we are going to make, not that we're making right now, but we're going to make into a log. And then we make the changes on disk. If the power cuts out while we're making the changes on disk, I just said something that's confusing. The log is on disk, so we make these changes out to a log on disk. And then we make all of the changes into the file system, right? The inodes, the data nodes, the bitmaps, right? So that's the second stage. If there's a problem when we're making that second phase changes to the inodes, data blocks, or bitmaps, then we should be able to detect it by when we boot up again after the power goes out, walking through the log, seeing what operation should have been made, and then checking to see which ones were actually made on the disk within the file system, within the inodes, within data blocks, or the bitmaps. Okay, so let's go through some examples of this. So now we've added a journal onto the head of our list, as you see on the far left, and that is a circular log, basically a ring buffer, but instead of holding kind of a single size of data, it includes a number of data items that we're going to log in there, which are things that we're going to, changes that we're going to make on the disk. And we're going to walk through the move example again, where we want to move B from directory A into directory C. And so what's the first thing that we do? We start adding those operations that we're going to make into the journal. So the journal is on disk. So we start a transaction. A transaction is a atomic collection of modifications that we're going to make. So the first modification is effectively to change inode A to remove B from it, right? So here I say that we maintain a diff, right? So we maintain the data that was in A and what we're going to change it to effectively. Then we can make the second update into the log, and that's going to include adding the inode B into C. And after we do that, we can effectively say, okay, this is all the modifications I'm going to make for this single operation, so I'm going to commit this transaction into the log. The transaction only means something within the log, within the journal, if it has a start and a commit. So we'll see where that comes in later. So we've basically made our modifications to the log at this point, and now we're going to go and make those modifications out to the inodes on disk. So now we're going to make a couple more updates to the disk in the second and third updates, right? Cool. Okay. So that is fine. The whole idea here is effectively that we break loose modifications in two stages, as I said, make the modifications to the log, lend those to the rest of the disk, the actual file system. And now we have to answer the question, great, we know what a log is, we know what it does, what about crashes? Right? So if the system crashes, we need to ask, what if it crashes during the file system index inode or data updates? What if it happens between logging and those other disk modifications? And what if it happens during logging, right? We're adding this logging thing. Now we're adding different places that these different crashes can happen. One thing that's really important here is that the file system needs to make sure that the right to commit the transaction into the journal completes before we end up writing the rest of the data out onto disk. So what I said before about kind of arbitrarily kind of doing the updates to disk in different orders, that actually doesn't really happen here. Okay, so let's go through another examples, and I'll go over that again. Okay, so we do our writes 1 and 1 prime out to disk. We say what we're going to do. Then we do our modification to A, but then we get a crash, right? So we are not able to actually update C. All right, so what can we do here? I want you to think. We have a log, the system crashes. On boot up, we still have the log because it's on disk, and we have the modification A, but not the one to C. Pause for a second, think about what we can do to fix up the file system at this point. Pause, come back. So of course what we can do here, we can go through the log one entry at a time, and we can say, oh okay, we were modifying A to remove B. We can look at that inode A and see that B was already removed. That write did go out to disk. Then we can look at that second entry and say, oh, well we were supposed to modify inode C to add B. Right, to add the reference to the inode B. That is not reflected on disk. We do not see that inode C has that. So at that point, when we're booting up, we could replay the log, make the modification to C, and therefore have a consistent version of the file system from that point on. So we can apply the second journal log entry to apply that 3 update to the file system effectively, right? Okay. What happens if we get a crash between when we write the journal and when we make the modifications to the other file system data structures? Think about it for a second. Come back, pause, come back. So what happens if we get a crash after the log has committed but before the updates? Well, that's simple. I mean, we just apply both of the updates in the log and we have a consistent version for the file system, right? This is interesting because it means that it doesn't really matter how many of the modifications to inodes to bitmaps to data on disk actually get applied, so long as the log is completely correctly applied and we've committed it out to disk, we can actually update all those data structures within the inodes, bitmaps, and data to make a consistent state within the file system as if those modifications all had been made correctly. But that definitely raises the question, what the heck happens if a crash happens while we're writing the log, right? While we're actually journaling? Well, okay. So in this case, we are not able to complete writing out to the log, so we did not add in that second entry. But because we didn't add in the second entry, we also have not added in the commit, right? So we have not actually committed the log out to the journal. So that means that when we boot up, we'll be able to see that there's an incomplete log. Therefore, we cannot replay any of it out onto the disk data structures, and it's effectively identical to the case where we just didn't do any of these operations whatsoever. So you can see this feels like that notion of atomicity that I talked about before. Either the file system looks like we committed all of these operations out to the disk, or we did none of them, right? The log facilitates that. Now the question is, how can the file system actually detect whether we have committed this entry in the log, right? This transaction in the log. So think about that for a second, pause, come back. So, I mean, we simply just write out to the log after we have added the 2 differences in this case. We wait for those to be written out to the disk. Then we add another update to write that commit out to the log, right? So that's really important. It's really important that we actually wait until all the previous updates go out to the log before we actually do the commit, because we need to make sure that the entire log entry is out on disk before we say that it's committed, right? So then I'm not talking about kind of inode updates, disk block, bitmap updates. I'm just talking about the log, right? The journal itself. I need to make sure that everything's there before it's committed. So we can effectively just kind of track whether that commit, we can keep like a numerical identifier, a 64-bit value for each transaction. And for every start of a specific transaction, we should see the commit. If we don't see the commit, the log hasn't successfully been written out before the crash happened. The downside of this, unfortunately, is that means that you have all of these writes that you need to make it into the journal, into the log, and then you have to wait for all of them to commit before you can actually do the write to say that you've committed. But there are clever ways to get around that by just checksumming each of these operations that we send out and then seeing whether checksumming the entire entry that we want to write out and then checking whether a partially written log actually matches that checksum. I'm not going to go into details here. If you're interested, ask in the FAQ and I'll provide links to the papers that go over that. Okay, so now we have a number of groups of updates. We want to add in the transaction start and all of these log entries for all the operations that are going to be performed, right? Then we want to write that we have committed that transaction out to log. At that point, we kind of know all of those updates are going to happen to the disk, whether we crash at this point or not, right? Because if we don't crash, then we actually do the file system updates to the bitmaps, the inodes, the data. And then we essentially progress the journal, which is to say we just say, okay, yeah, we've committed that entry. So we essentially update the transaction ID of the overall file system to say that that has been committed. Okay, so this is journaling. It allows us to essentially have this separate way of tracking all of these nodes that should get written out, all of these updates that should get written out, and to allow atomicity by allowing them to effectively all be written out or none of them, facilitated by this kind of two-stage operation of writing out to the log, to the journal, and then to the rest of the file system blocks, right? The downside is, of course, this causes extra writes. We need to actually write to the journal itself, and that's not free, right? So this is not great. It would be great to get around that. One way that practical systems have gotten around it, ext3, for instance, they basically said that you can log only inode updates in the journal to mitigate the overhead of data updates. That means that all of your data updates on disk are not tracked in the log, are not tracked in the journal. Therefore, you could end up with corrupted data within files, but your file system structure with respect to the inodes will always be consistent, right? So this is kind of a halfway point. At least you aren't going to be kind of losing portions of your data structure of your file system or needing to do FS checks that are really expensive when you boot up, right? But your data could get corrupted, which is not awesome, right? Okay, so journals effectively provide an overhead on top of file system operations, but they do provide crash consistency. So this is really, really important, right? And they effectively allow us to, at boot time, instead of running a full FS check, just replay the log, effectively replay the journal, which is very, very fast, effectively. Okay, so is there any way to get around all of these kind of extra writes that we're doing for the journal? It's not clear if there is a way, right? But we actually already saw a technique that kind of starts to look like being able to have consistency without needing the journaling. And that was actually copy on write. So copy on write file systems are kind of these are in what are most of kind of the next generation file systems. So Btrfs, ZFS, these types of things. They tend to be copy on write based file systems. And this just takes the observation that if we copy and write everything, and we're careful to effectively write the referenced data and the referenced inodes, then write the inodes that reference them, then we end up with a consistent on-disk data structure kind of by default, right? The difficulty, as we'll see through a few examples, is that this requires that we copy and write not just a single inode or a single piece of data, but usually the entire index structure on up to the root. This can be quite bad. There are definitely systems, and these kind of next generation file systems don't do that version of things, and I'll talk about one trick that we can play to get around it. But a naive application of copy and write is going to be complicated. Let's look at why. So you see the tree in the bottom. That's kind of a logical tree where we can see A, B, and C are directories. D and E are files that reference data, which is the purple part, right? The data pointers are blue. The inode references are black. And we can see on disk, we have those inodes A, B, C, D, and E, followed by the data blocks, right? And I just have drawn out all of the pointers that you see in the logical structure above. Now what if we wanted to execute move of the D file in the A then B directory into the A then C directory, right? So copy on write means that we're going to need to modify both the B directory and the C directory because we're moving D from B into C, right? So because we're doing copy and write and we're modifying B and C, that means that we need to make copies of them. Here I've annotated those copies as B prime and C prime, okay? And you can see that they have essentially the updated pointers to contain D moved over to C from B. But that's not enough. If that was the only cost, it wouldn't be that bad. That's not enough because you can see that A still points to the old versions of B and C. So what we actually need to do is also copy A into A prime and set up the file system to understand that that new A prime is the real root of the file system now, right? And because all of these modifications are effectively being done by that single modification of the file system's reference from A to A prime, they are done atomically. So long as we know that B prime, C prime, and A prime are all written out onto disk, when we update that reference to A prime, we know we have atomic updates to the overall file system. But if you remember what we were talking about when we were talking about JFFS for flash-based file systems and kind of the ring buffer of data structures, that produces garbage, right? Now these A, B, and C directories are no longer referenced, right? So we somehow in the future need to build garbage collection into our system. So these copy and write systems, garbage collection is always kind of an inevitable complication that follows through, and we need to come up with ways to fix them. So now if we wanted to do another operation where we effectively append onto the end of the D file, then we're going to have a comparable operation where now D is going to need to be updated into a new version of D, D prime, because we're adding to the size of the file system and changing the index of D to point to new data, right? So now because D needed to be modified, well, that means B double prime might need to be modified. There actually might be cases where B double prime might not need to be modified, but again, because we created this new D prime, the B prime is pointing to the old D, not the new D prime. So we need a new version of B double prime, new version of A double prime, and then atomically we need to update the file system reference to say, okay, the actual root is A double prime, right? And you can see that this is just appending onto the file system towards the end for each of these different operations. And of course that, comparably as we saw before, generates some garbage in the system, again motivating the need for garbage collection. So I'm not going to go through copy and write file systems in much detail. There are a lot of demons here that I'm not going to go into. I think you all should, because it's very interesting stuff, and it kind of lets you go into the itty gritty details of file system implementation, but I'm not going to do it now. Okay, so copy and write, let's summarize it for a second. When the root index is updated, the file system reference to where the root is, all of the data structures that are on disk are now consistent. That's because we make sure that we've written all of those modified data structures onto disk before we do that update. This does require garbage collection in some way, similar to JFFS. JFFS was very simple because it just had the head and tail. Everything in between was either erasures or data that was valid, depending on which side of head and tail you were on. We really can't do a simple continuous log for a real file system because you end up copying too much data. So garbage collection ends up being a relatively complicated operation. We saw here that you kind of need to do copy and write all the way on up to the root, which is a lot of disk writes just to do one write. There are some systems that have combined copy and write with journals for a lot of those metadata structures, a lot of the inodes. And in that case, it allowed us to keep some of the old inodes around and modify them in place. And if there was some sort of a crash, we would rely on the journal to effectively give us some consistency there. So you have a trade-off effectively. Do you want to use copy and write for everything or just for data, right? Do you want to use journaling for some stuff where that cost of copy and write can get overbearing? You can imagine, for instance, that copy and write is used for all of the data on the file system, whereas journals are used for all of the in-place updates of the inodes on the file system. You can imagine a file system being implemented in this way. LBFS, the log-based file system, I'm pretty sure that's the name, virtualizes inode numbers to actually allow you to do kind of this allows you to not have to go all the way up the whole path to root in a really, really clever way. But I'm not going to go into that now because I don't want to go in too deep. Now, the thing about copy and write, you are modifying a lot all the way up to the root if you're doing true copy and write all the way through. It is a lot of disk writes, but it is also a lot of very parallel disk writes, right? You can make all of these requests to do those operations all at once. You just need to make sure that they are all out on disk before you update kind of the reference to the root of the file system. Okay, now, I want to kind of back up a little bit and talk about consistency again, because this is a really important idea, and it's something that you see in a lot of different domains, okay? So we've looked at it in the instance where you want to separate the modifications made to the data, and this is kind of a lot of our file system APIs. A lot of those are in memory. And then separately, you have the notion of what is on disk and what is visible on disk. So there was this notion of atomically updating what's on disk, or doing none of it, right? This is kind of a transaction-based semantics where nothing's committed or it all is atomically, right? So you may actually, as a program, see that you've written to something on disk, but it may not actually be out on disk. There's a little bit of a window between when you do your write, your modification to the file, and when it's out on disk. There are programmatic APIs to remove this window, like fsync, but generally this is an issue. And consistency usually has this problem. You have some operations where you might have some inconsistencies if they were made directly. So you need to decide when to make them or how to make them so that the actual backing data structure when accessed is consistent. So this effectively means that we require that the final stored values, in this case out on disk, abide by the data structure correctness requirements, i.e. it is consistent. In distributed systems, we have exactly the same problem. I can ask one system to send me my profile pic, it could give it back. I can ask another server to send me my profile pic, I could get it back. If they're the same, we have a consistent view of the kind of data structure tracking profile pics across the two servers. However, it might be the case that I update my profile pic, on one server, but that change has not been propagated to the other server. So we could have inconsistency in distributed systems. So crash consistency is one instance of this broader notion of consistency, and this is why I wanted to go over it in this class. The whole idea behind crash consistency is that we want to avoid inconsistent data structures on disk so that when we boot up, we know that we have a proper functioning file system. We tried to add atomic updates whereby we either update all of these blocks at once or not at all, kind of a transaction style semantics. And again, this is the notion of consistency is an important concept in many different domains. In parallel data structures, it's very important, often in lock-free systems called the linearizability. In distributed systems, as I gave in the example in the previous slide, we have this issue. In databases, they fundamentally must be reliable and must have a similar notion of crash consistency. So this is a very general notion that you probably should understand as a computer scientist. Don't be afraid as you're going through your own work to look up different forms of consistency. So thank you very much. Hopefully this was interesting. This closes out our talk about file systems. Hope you enjoyed it. Talk to you soon.